Hey, good to have you back again. So let's look at this question. We're going to compare, in this lesson, we're going to compare simple interest with compound interest through an investigation, an example of a case, and then we're going to go through and analyze which one is better in the long run and be graphing it and see what that does. We have two buddies, Ben and Jerry, both received $1,000 gift from their grandparents. And Ben goes and buys $1,000 simple interest GIC, guaranteed investment certificate with 5 years term at 4% paid annually. But Jerry goes and buys the same GIC at the rate of 4% compounded annually for 5 years. So one is simple interest, the other one is compound interest, both same rate, but we want to know what happens in terms of the total accumulation for each and then which one is better. Now, the simple interest accumulated formula for that is given by this right here, A equal to P times 1 plus RT. And the compound interest based on the accumulated amount is A equal to P 1 plus R divided by N to the power of NT. And I've created this table here, and we're going to go through each of the years and see how much each one will make and then compare and contrast. So what I like to do, write up the actual formula inside of this table. Okay, so plug in numbers completely with the formula so you can see it, and then you can go ahead do the math on that. So that's what I'm going to do for each one. Let's do that. So for Ben, we have A equals P is 1,000, 1 plus 0.04, close the bracket. Because it's a 1 year, that's all it is. And whatever the value is, that will be it. And for Jerry will be the compound interest formula, but it turns out to be the exact same thing. 1 plus 0.04 divided by 1 to the power of 1. And you can see what the answer will be. And I want you to go ahead and pause the video and fill this table with this formula with numbers plugged in into each one, and then see which one is better and see the each values, and so we can compare and contrast. When you go through the table and plug in then the values for Ben and Jerry for simple interest and compound interest for Jerry, and I did the year 1, 3, and 5. I wrote up the actual formulas. The other ones I just calculated the values, and you can do the same. And you notice that the first year, they are the same. So this value here and this value, they're both the same. But as you go through the years, year 2, there's a little bit of difference. We got 1081, we have 1080, so $1 more. Not much, but it's going up. But notice what is happening as the year goes by. The differential between the values are getting larger and larger. First one was what dollar, now it's $4 or $5, and then you go up to $9, and then by year 5, Jerry is $1,216.65. Now you're looking at between 9 and then all of a sudden is $16 differential between the two, which is actually substantive. Now, if you continue this to 30, then you'll see what I'm talking about, where the power of compounding becomes really, really obvious. For the simple interest, get $2,200 for Ben after 30 years, but for Jerry, let's do the math for Jerry. That would be 1 plus 0.04 to the power of 30, because n is 1. So, and then you just plug numbers in and let's see what you get. 3,243 and 40 cents. Look at the differential between the two values, where you have $2,200 versus $3,200. That's approximately $1,000, a little bit more than $1,000 differential when you do compound interest. Okay, using a compound interest. So this is the power of compounding, and I want to now show you graphically how they look and they compare. So let's do that now. So I'm using Desmos to graph what we just had. Okay, that's what we did. And for each one, so y1 represents the accumulated amount for the simple interest, and y2 is the compound interest accumulated amount. And look at the graph. One is pinkish, the other one is green. The first few years, the differentials are not a lot, right? So 81, 80, you got $4 differential here between that. You got $9, about 10 bucks. Then it goes to $16, and then it starts going higher and higher. And what I did, I hit the 30, and then I did do a 20 just to get in between. So 20 years is 1800, one is 2191, which is about $300 differential. But by the time you hit 30, is more than $1,000 differential. And look at this point here and look at this point there. These are the differentials between the two that you can see, and that's why the compound interest is way more powerful than simple interest. It's one of the 7 or 8 wonders of the world, as Albert Einstein says it. So this is the graph. The first part of a graph is basically matching the simple interest, and simple interest creates a linear function. So if you actually graph this pink, connect these pink dots and put a line right through them, it becomes a straight line. And the y-intercept will be 1,000 because you start with $1,000. And so as the compound interest, the graph starts there, but then becomes exponential. That this curvature that you will see, that exponential functions supersedes any linear or a polynomial functions by far. So this is the graph, and it becomes a linear graph line for the simple interest, but becomes exponential, which is a huge curve, and then it shoots up way faster than the linear. Now I'd like to show you the graph of both of these, and let's see how different they are. Let's look at the first one, which is the simple interest graph. So I'm going to graph this. I'm going to add a line and look what's happening. Okay, so this graph is really, really a straight line. So it's going through all the data points of the pink points. If I can zoom in, you can see it more, right? They're different, right? And if I now go ahead and graph the green, now the green is not linear. And because of that, I have to, and I know what it is because it's exponential. So it's not linear. It has to be exponential because I know it because it's the power of the variable is the exponent. So if I say exponential graph, and it shows me this beautiful exponential graph that goes through every single point there is. Unfortunately, is not changing the color, and I have no idea why, but that's what that is, okay? So if I change that again, yeah, here it is, and look at the graph. I'm going to zoom in again. I just want you to see the differential between the two. So basically, the first 2 or 3, the differentials are very, very subdued. The first one is definitely the same, doesn't do anything. The second one is very, very minute. That was about $1 differential between the two. But then after 30 years, look at that. I don't have to zoom in anymore, and you can see that it is just going. And the longer it goes, look at that. At the 50th year, the 50th year, this is the point right here, which will be 49.9, and then 7,113, and then this one is as linear with the same slope. Is just going to be around this area, which is about 4,000. All right, that's all I need to say. I just wanted you guys to see the graph, to see the differential between the two, but isn't this amazing? All right, now you can play around with Desmos like this, and you can actually explore different values for different simple interest calculations and compound interest calculations, and you do your own exploration, which I really suggest, I strongly suggest you go ahead and do that, because it's tremendous help in terms of understanding what the concepts is about. All right, be well. All right, that's all I want to talk about. I hope you found this useful. subscribe, like, comment below. Until next time, keep well and practice, practice, practice. Take care.